Today we're going to talk about aquatic chemistry, and we're going to focus on redox, oxygen, and pH, and a bunch of things. So first of all, stream water chemistry has similarities with rainwater chemistry. So rain can bring in some interesting chemical inputs, but it's also influenced by parent material, which is the geologic landscape that the stream is running through. And as water evaporates from streams and lakes, some of these elements can become concentrated. Also, as the stream moves through landscapes, water chemistry can be altered by chemical processes and biological interactions. And unlike seawater, river water varies greatly. So the ocean, there is variation in seawater chemistry, but it's a lot less variable than river water chemistry. There are controls on chemical controls on things like physiology, biogeochemistry, and how pollutants behave. And I'm going to talk about a whole bunch of different chemical factors that could be considered along a gradient from low to high. And so basically, I want you to think about the optimal range for a particular organism. And then I want you to think about what happens when those organisms are exposed to stressful levels, either on the high or the low end for that chemical, or a zone of intolerance. So at what point can the organism no longer survive because say salinity or the pH has gotten too high or too low. So this is just a nice kind of conceptual way to imagine organisms responding to each factor and then having to navigate the environment that is a suite of all of these abiotic chemical factors. So all kinds of materials are transported by streams. Gases like nitrogen, carbon dioxide, and oxygen. Dissolved nutrients, especially important are nitrogen, phosphorus, and silica. And dissolved inorganic material, so lots of major ions, cations like calcium, sodium, magnesium, potassium, and anions like chloride, sulfate, and bicarbonate. Or I think that's just carbonate. Sorry, I get those ones mixed up. But we're going to talk a lot about carbonate chemistry. So if I got that one wrong, I'll get it right in the future. Suspended and dissolved organic material. So materials can either be dissolved in the water column or they can be lifted up, carried, and then dropped again, suspended. There are suspended and dissolved trace metals. Then there's suspended inorganic material. So other major elements, things that wouldn't necessarily be considered nutrients, but might be, micronutrients, things that are important in small quantities like aluminum, iron, silica, calcium, potassium, magnesium, sodium, and phosphorus. So particles can be considered dissolved particles, things like protons, small dissolved molecules. They can be colloidal, which are compounds that are so small they don't really ever settle. And so viruses, human compounds, different parts of cells as they're broken down, polypeptides, things like pieces of mineral particles. Those might be lifted up and carried by streams, and they'll never actually settle out of solution until they reach the ocean. Or they can be larger particles that are called gravitoidal, which eventually they will settle out. So pieces of detritus, organic material, clay, and then you've got your organisms. So unless they are mobile, they will eventually settle. So things like bacteria, and then if they die, obviously they'll settle out, bacteria and other organisms. Okay, so we're gonna go through some of these water chemistry, these factors, things you can measure. So the first one is conductivity. So conductivity or specific conductance, and there are some slight differences between those two things. They're not exactly important right now, but they both measure dissolved ions in water, and they tend to be corrected to 25 degrees Celsius. And conductivity is related to total dissolved solids, which I'll talk about in a minute. But conductivity is the ability of water to carry an electrical charge. And this is because of both positive and negative ions that are dissolved in the water, and they come from surrounding geology and sources of groundwater, some from rain. Conductivity can also tell you if there's a lot of nutrients, things like phosphates and nitrates and ammonium, because those are also charged. Those are charged molecules. And so sometimes high conductivity means high nutrient concentration. Sometimes it doesn't. It can also indicate for things like saltwater intrusion or salinization, like from agriculture. Or road salt pollution. So because it's a measure of these ions, and salts are ionic compounds, they can sometimes be correlated. Conductivity can also, if it's really high, tell you, it can indicate for other types of pollution, but not always. So it's a big kind of messy measure that can tell you that a lot of different things are contributing to it. And sometimes you have to do follow-up studies to figure out, why is the conductivity so high? Is it nutrients? Is it pollutants? Is it salinity, something else? If it's salinity, that's important because brackish water is often not suitable for a high number of species. And so conductivity can tell you if it's brackish. And in general, because we live in a salmon region, I'll kind of talk about what salmon prefer. Most salmonids prefer conductivity values less than 150 microsiemens per centimeter. So, and you can kind of see tap water. Sometimes tap water can be up to 800 on this, like this nice graph on the side. Distilled water is very low, and that's because all of the ions have been removed from distilled water. And seawater values are really high, 55,000. Okay, so I told you conductivity was related to total dissolved solids. TDS is a measure of cumulative dissolved ions, including uncharged molecules. And it's mainly due to the weathering of sedimentary rocks, but can also be influenced by freeze-thaw. So when lands are frozen and then thaw, it kind of breaks things apart and contributes to mechanical weathering. Increased runoff, so surface runoff when rain falls and doesn't sink down into the ground, but runs off instead, that can tend to both bring in suspended and dissolved sediments and things, but it can also dilute the total dissolved solids. So rainwater doesn't tend to have a lot of dissolved solids. Total dissolved solids helps us understand whether the water is considered soft or hard. So soft water has low concentrations of calcium and magnesium, and hard water has high concentrations. And these things are important because mollusks and crustaceans need calcium for shell formation. So they're not going to be found in soft water systems. Here are some cumulative curves for a bunch of different ions found in fresh waters. And so basically this is showing you like the range in concentrations that you see across lots of different systems for these different ions. And so, total dissolved solids, of course, that's the highest because that is everything that we're looking at. And then you have things like, let's see, the solid green line, that's sulfate. And so some systems have pretty low sulfate, and some systems have pretty high sulfate concentration. So kind of what you're seeing is as the line becomes more upright, then it's less variable on the landscape. And as the line is kind of flatter, means that there are some systems with really low values reaching out to other systems with really high values. And so concentration is shown on the x-axis as a log scale. This is kind of a funky way to talk about this, but it's in the book. So, all right, so moving on to pH. So what does pH stand for? There's a lot of debate out there. Some people call it the power of hydrogen. The German use the word potens, which means power. The French use the word puissance, which means power. Latin, you could either say it's pondus for quantity of hydrogen or potentia for capacity of hydrogen. Anything, it's about hydrogen, right? Something about the potency or the power of hydrogen. And so it's really a measure of the hydrogen ion activity. So it's very closely related to the hydrogen ion concentration, but it's this activity value instead. And so to measure it, you need to know you take the hydrogen ion activity and the negative log 10 of that gives you the pH value. And so what this does is it tells us whether a solution is acidic or basic. Acidic solutions are very low on the pH scale, 0, 1, 2, 3. Basic solutions are very high, like 12, 13, 14. 7 is neutral, neither basic nor acidic. And it's again a log scale, meaning that each step on the scale is a factor of 10. So going from 7 to 8 is more like going from 7 to 70 than it is just one shift. Okay. So black coffee at a pH of 5 is 100 times more acidic than a glass of water. Okay. If water is like drinking water is about neutral at 7. Salmon tend to prefer a pH of between 6.5 and 8.5. So we talk about this as circumneutral. They can handle things slightly more basic than they can acidic. Okay. And here's some pictures of where, the tolerance zones for different organisms. And so you can see that humans can handle water. I think this is, I assume, for drinking between about 4 and 10. But fish are about 6.5 to 8 to 9, something like that. Acid rain, normal rain is slightly acidic. Normal rain is around 5. But acid rain can be between 4 and 1. So it can be down by like battery acid. Fish die in pH solutions of lower than 3. And crabs, snails, and mussels like more basic waters. They like, again, those softer waters that have more calcium and magnesium. Plants too can handle just below 7 all the way up to 12. And again, fish will die in really basic waters. So acid precipitation can reduce the pH of stream water by several orders of magnitude. Acid solutions also increase the solubility of toxic metals, which can be damaging. And when we're increasing CO2 concentrations in the atmosphere, that leads to increased CO2 concentrations dissolved in water, and that decreases the pH of water. And the reason is because of this kind of carbon, carbonate buffering system that I'm going to talk about in a second. So related to the pH scale is this measure of both alkalinity and acidity. And these are measures of the capacity of water to react with strong acids and bases, respectively. So for example, if you have a high alkaline lake and acid rain is added to it, that acid rain can be neutralized. And because of this, and I'll show you this figure, because of the alkalinity, the pH can remain neutral and aquatic life will be harmed. However, if you have an acidic lake or a low alkalinity lake, the acid rain is not neutralized. The pH then drops below 7 and most of the fish die. And so alkalinity is a really important measure. It's related to the pH scale, but it's more of a capacity to buffer change in pH. And okay, so I feel like that's what I should talk about next, but instead I have the slide on hardness. So I'm going to talk real briefly about hardness, again, related to total dissolved solids. Hardness, though, is just the sum of magnesium and calcium ions, and it indicates the ability of water to precipitate soap. It influences domestic water supplies. So hard water causes scaling. I have really hard water at my house. So I have scaling on my teapots and coffee cups and my shower and things like that. And it interferes with the ability of soap to create suds. So hard water, you have to use more soap to get kind of suds. Scaling decreases the efficiency of water heaters and can cause vegetables to lose flavor. So oftentimes people will add water softeners, which are basically ion exchange resins that pull these ions out of the water. They remove magnesium and calcium ions. And that's exactly what deionized water is. So it's much more extreme than what people do to soften the water in their homes. Deionized water removes all ions, all positive and negative ions. So DI water has no ions, and that's why it's used in laboratories, because it doesn't interact as much with reactions. Total suspended solids and turbidity are significantly correlated. So this is a little different than total dissolved solids. Turbidity is the light absorption ability by water. So both dissolved and suspended materials can cause turbidity, which is kind of like how hard is it to see through. And total suspended solids is determined by filtering the water out and weighing it on filter paper afterwards. And you can then separate the total suspended organic material and the total suspended inorganic material by combusting the filter. Okay, so to really understand aqueous chemistry, well, I'm going to stop here because I think I'm missing the slide on the carbonate cycle, and that's really important. So I'm going to go back, I'm going to add it, and let's take a little break. Okay, so real briefly, this was the slide I was looking for, and I realize I'm talking about it next week. So, but I am going to just say real briefly that this is how the kind of buffering system in an alkaline lake works. And so, what you can see is the pH scale on the bottom and the fraction of the dissolved inorganic carbon. And so, when you add CO2 to a system, it's going to push things toward the pH, the lower pH values. And if you have a system that's neutral and it has a lot of bicarbonate in it, and you add acid rain, what that does is the bicarbonate dissociates, and then it leads to less of a change in pH than you would predict because of that buffering capacity. It's the same thing that we have. We have a bicarbonate buffering system in our blood too that helps to keep our blood really, really regulated. And so basically the system buffers for changes in pH. So I'll go into more detail next week.